The topic I selected for today is one of our topic in Politecnico di Milano, and starts from our experience in waterjet machining in general. So this is the reason why this is the title of the presentation. In reality, what I would like to show you is or are some new applications of waterjet cutting in particular towards high precision manufacturing by means of this technology. I don't know if you are already aware about this technology. In any case, the target of today is to divide my presentation in two parts. The first one is for giving you the basics of this process, and some of these basics are related to macro applications. And at the end of the first part, I will show you some micro applications or high precision applications. Sometimes I prefer to use this term instead of micro. Also because you know that the term micro means different things depending on the process or depending on the field you are approaching. So I start with the very basics of this presentation, but first I have to comment a little bit about the logos. This is the logo of Politecnico di Milano, obviously, but we have a couple of other logos. This is the logo of Waterjet Laboratory in Milano. It is quite a long time that we are involved in waterjet machining, I think about 20 years. And this is the logo of a spin-off company which has started from the experience in high precision machining by waterjet. So this is mainly the topic of today. Here you can see a movie which has been carried out by one of the multinational companies involved in waterjet machining. This is a typical pump, a redundant pump. You can see the piston which acts inside the machine. And the principle is quite simple because you have oil acting here. You can see the oil in red when it is under pressure. The oil pushes the piston on one side and then to the other because you have a valve which directs oil to one side or to the other. And the piston has two faces. The face on which the oil is acting is larger than the face where water is acting. Water is acting here. So by means of this difference between the areas, there is a difference of 20 times. You can multiply the pressure, basing on obviously a balance of forces. This way, the water is sent to the cutting head. This is the cutting head. Water comes here. This is a tube. This tube is quite long in order to stabilize the water. And you have a stream of water inside a couple of orifices. The first one is called the orifice, more properly, or primary orifice. And this second one, this one, is the focuser. You need two orifices because passing through the first one, you change the pressure energy into kinetic energy. And then you need another orifice, which is quite long, in order to make a mixture between water, air, and abrasive. We will see more details later about this. This is an animation in order to explain how the pump works. I will come also later on this concept, but as I told you, the principle is quite simple. So the pump pressurizes oil, and you have a valve for distributing oil to both of the sides. And then you can see here the color, the blue. When the blue is dark, it means that you are pressurizing water. And then you need also an accumulator. Otherwise, you have, at the end of the stroke of the piston, you could have problems because your signal of pressure decreases quite to zero. And this is not good. This is not good for the machine because you risk fatigue problems on all the components of the machine. And also it is not good for the process itself because if you have a fluctuating signal, you risk to have some problems on the parts in terms of roughness, for example. Okay, I come back to something which is more general. It is a kind of advertisement, I know, but I think it is useful when you have to show this technology to someone who has never heard about that. I don't know if you already seen some application of Waterjet machining. Can you tell me if you already know? Nobody?
No, we got our samples in the university Waterjet.
Okay, okay. But you know also what is inside?
Inside the machine?
Yes.
No, I thought that they are using reciprocating pumps, but
yeah.
It's different here.
Yeah.
I've seen some cut stones for gardening into shape with Waterjets.
Yeah. This is quite typical application. For example, in Italy, we have many companies involved in cutting stones. When you see some marble cut into very tiny parts, but the difference is made by the trajectory. When you see round parts, many times they are cut by Waterjet because it is difficult to use wires. Also diamond wires can do that, but they are quite thick. The advantage of the jet is that it is quite small. So the standard jet has a diameter of 1 millimeter. But as I will show you, in case of high precision applications, we have a final jet after passing through the focusing tube of 0.2, and we are trying to reduce this diameter down to 0.15 or 0.10. So this is the target. And as you can see here, Waterjet can cut many materials, so it is very flexible under the point of view of the target you want to cut. This sample has been cut by putting all together all these materials. So this is true, we have cut through everything. The jet suffers when you have empty spaces between one layer and the other, because after cutting the jet still has some energy, but if this energy is not confined by another material, another layer of material, the jet spreads, and so it becomes wider, and so the specific energy is not enough for carrying out a good cutting operation on the other layers. But if you put all the layers all together, you can cut something like sandwiches. And sandwiches, in this case, it can be used both for technical reasons. So sandwiches made by layers of titanium and carbon fibers, for example, for the aeronautic field, but also sandwich as food, because Waterjet can cut, as you can see here, also food. Obviously, in this case, you need a machine which has very controlled waters, obviously, in order to cut food. But if you think about soft materials, like the bread of the sandwich, this is a typical application of Waterjet because it is very discrete, so it applies a very low force. So the material doesn't deform under the force of the jet. So, you know, I think that everybody of you has tried to cut something like a sponge with scissors. You know that it is very difficult because the part deforms and you risk to carry out a very bad part, bad quality. But this is the work of Waterjet, because you can cut rubber like this. These are some polymeric sponges which are used inside dampers for furniture. You know that you like when your furniture is very smooth when you close it. So inside the furniture there are some dampers, and inside the dampers the elastic part is made of rubber. And rubber is difficult to be cut in a very precise fashion, but pure Waterjet can do that. So as you can understand, we have two main branches of Waterjet cutting. Pure Waterjet, when you use only water, and abrasive Waterjet, when you want to mix also something which can act like a real cutter on your material. So typically on stones and on steel and metals, you need to use also abrasive, because you want that each single particle takes away a small amount of material, like a real tool. Obviously, the jet acts like a stochastic tool, because it has not a defined geometry. This is another characteristic of Waterjet. If you think about a mill, even if I have to tell something about also micro milling, because I'm involved also in micro milling. But if you think about standard milling operation, you can understand that you have a very defined tool with a precise geometry. And this tool is able to reproduce its shape, its geometrical shape on the part you are machining. The jet, the water jet, is not acting like that because it deforms, it adapts to the characteristics of this material, so it bends. So you risk to create some convergent walls. If you go very fast, you are distributing your energy specifically on a certain length of your material by distributing very small amount of energy per unit of length. And in this case, your energy usually is not enough for carrying out a straight curve with the parallel walls. In this case, you have convergent walls. But usually, in mechanical application, you don't want that. So, as I can show you later, we want to compensate this kind of error. So you can see some details. Also, leather can be cut. Another typical question about Waterjet is how can water cut leather or also paper? Because the risk is that you make the part wet. But if you cut with a very thin jet, and in this case we are using only the orifice, so as you can see here, we don't have the focuser. We can have a jet of 50 microns in diameter, and the power is enough for going very fast, many meters per minute, and this is enough in order not to wet too much your material. So you can cut also paper. In case of paper, the feed velocity of your cutting head is very, very high. In reality, you keep the cutting head fixed in a position, and you have the material which flows under the cutting head very fast. Okay, marble. And here we can see some other typical situations of Waterjet. As you can see here again, you have the jet. And typically the jet has, after cutting, has the characteristic to be very detrimental, very dangerous for your fixture. So another characteristic of Waterjet is that every time you are cutting a part, you have to develop a specific fixture in order not to be damaged. Especially if you want to make a very precise part, or especially if you want to make many parts on the same fixture. So you have to apply a kind of fantasy every time. And if you are very clever under this point of view, you can have a very big advantage. So in the case of the spin-off, we invented some kind of fixtures in order to solve some problems like this. So the principle, here you can see again, so I don't stay here too much, but you can see now some numbers. So these are typical numbers of water pressure in Waterjet plants, so 380 megapascals. But there are also plants achieving a pressure of 600 megapascals, so 6,000 bars. So the pressure is absolutely high, and so this is the reason why you have so much energy, which is directed to the part. The problem is how to manage this energy, how to focus this energy. And the velocity is another typical number which is quite incredible. You know, when you talk about non-conventional machining, if you think about the different non-conventional processes, each one of these processes has a typical quantity, typical physical quantity, which is quite non-conventional. In the case of Waterjet, I talked about pressure, but if you think about the transformation of the energy from pressure energy, I said, to kinetic energy, in reality, the jet is able to cut because it is fast, not because it is pressurized, because the jet exits in air. So when it exits in air, the pressure of the jet equals the value of the pressure of your environment. So in reality, which makes the jet very powerful is this value. This is the order of magnitude. Obviously, depends on many things, but this is true. We have measured in the past with laser Doppler systems, so we achieved velocities depending on the pressure. Obviously, we will see the equations later in the second part of the presentation, but we can achieve in standard application even 500 meters per second. And as I told you, I like to give you some tips, and I will come also later with some concepts coming from physics in order to enforce. Do you have a question? Yes.
What was the highest peak velocity that you've been applying? I mean, you pointed out before that it depends also on the material, but just the maximum that you've been.
You have to think that the velocity depends on pressure through the Bernoulli equation. So this is the basic point. I will enter into these details later. If the question is what are the parameters you have to use if you want to cut a certain material, velocity, as I said, is the physical quantity you want to obtain, but you have to adjust the pressure. And it depends on also the productivity you want to obtain. So every time you have to cut a material, obviously you have to think about the hardness of this material and the density. These are these two physical quantities related to the material are the basic ones for Waterjet. So if the material is more dense or harder, you have to apply a higher pressure. But you can also act together with the feed velocity of your cutting end. So if you see that you have not enough specific energy per unit of length, you can reduce the cutting speed. So every time you have to manage with these parameters. You have also other kind of parameters which are more similar to design parameters of your machine. I mean, you can design a machine able to handle very large orifices. Typical diameter of the orifice in Waterjet application is 0.3 millimeters. But if your machine, your pump is very powerful, you can use also large diameters, so 0.5 for example. This way, as I told you, you have the velocity depending on the pressure through the Bernoulli equation. Once you have the velocity, you are multiplying the velocity by the area. And in that case, if you have a larger area, you are discharging a higher flow rate and so a higher power on the material. So this is a very brief overview. I hope to.
I was more thinking of, since you've been referring to what is approximately the maximum pressure that we can obtain, what might be the maximum feed velocity a machine can actually, or the machines that you have, that they can just do independent of whether it suits the application, just what's the maximum that we can expect?
Okay, so if the question is like this, it is more a question related to the machine. So how fast can be a Waterjet machine? Because on the one hand, you have the cutting principle and the energy you have. On the other hand, you need to move the cutting head in order to carry out the feed rate you want. But I discussed before about energy, because energy is the most important part. Usually, typical machines are not the bottleneck of the process, in the sense that the cutting velocity, I will show you some cases later, but can be a couple of meters per minute. So if you think about laser machines, are order of magnitude faster. When you cut with only pure water, as I told you, this velocity can increase, and so in that case, your machine has to carry out a velocity of 10 or 20 or 30 meters per minute, which is still not so much compared to other technologies like laser. But we will see later that micro Waterjet can be comparable with some lasers in some cases, because you know, laser suffers some problems of reflection from the part. And also, when you talk about laser, you have to be careful, because we have many sources of lasers. So every time we have to specify what kind of source. In micro applications, usually in case of laser, you use femto lasers, so very short impulses. And in that case, the field velocity of that laser is not so much, and Waterjet can be competitive. Is it good? In any case, I think that I will add some other details later. So now I would like to touch the points which are important in order to increase the capabilities in terms of precision of Waterjet machining. I start from a very challenging and very difficult to solve problem. Because when you want to cut hard materials or dense materials, you need abrasive. But as I told you, if you want to focus the jet on an area of 0.1, you can understand that the grains of the abrasive has to be very small. A rule of thumb says that you have to dimension the diameter of your grains by thinking that you can afford a maximum of 2-3 grains in parallel inside the focuser. This brings you to use very fine meshes like this, 350, and these are like powders. And as you know, powders are hygroscopic, and so it is very difficult to bring these grains, avoiding clogging in the tubes. So this seems a very silly problem, but in reality this stops the operation. So if in a certain moment you have a lack of abrasive, you are damaging the part, and you have to throw away the part, and then you have to stop the production, you have to clean it up, and so it is not industrially feasible. So you need to invent something new in order to be able to bring the abrasive to the cutting head. Usually, the cutting head sucks air by means of the Venturi effect. So you have to think about a stream of water passing through a chamber. In a stream of water like this is able to carry away, to bring away the air outside the cutting head and outside the focuser. This produces a vacuum pressure inside the cutting head. The vacuum pressure sucks air, and this air is able to push the grains of the abrasive inside the cutting head. This is a typical way used in Waterjet machine. So it is not gravity. So gravity is not enough. So air is much more effective. The problem is that once you have air, you have to deal with this media, because at the end, air will mix together with water, and in a certain way, you are distributing the energy of water, which is dense, towards a medium which is not so dense in air. Obviously, it is not able to cut. So once air has finished its work, in reality, you would like to take it away, but usually it is not so simple to do. Or you have to invent some other ways to bring the abrasive to the cutting head. And here you can see another keyword. If you want to be precise, you don't want that your mass flow rate of abrasive fluctuates. So usually, typically, the Waterjet machines are in open loop. So this means that you calibrate an hole through which the abrasive passes. But if something happens, for example, vibrations of the cutting head, when you have to be fast, you know, when you have to carry out a corner on your part, obviously you have vibrations, you have inertia. In that case, something is happening to your feeding system, and the risk is that the flow rate is not stable. And again, even if it is stable, your machine on a corner has to stop, because, for example, you have to stop one axe, and you have to accelerate the other one. So you have a moment where the machine is stopping in a certain position. In that case, your jet is able to take away more material, and you can see the sign on the part. So there is a strict relation, as I told you before by answering to the question, between the energy and the way you use this energy. So standard solutions with standard machines are not enough for high precision. They are enough for cutting stones, for example, for cutting some parts of the floor, even if they seem very precise. But if you have to achieve a tolerance of 10 microns, for example, they are not enough. So you have to better design also your machine in order to be able to manage the energy. And if you look at this part, this is the bottom of a typical shape. This is a gear. You can see here that the jet is not so precise at the bottom because it bends. So when it achieves a corner, the back, the last part of the jet which is touching your material is removing more material on one side and less material on the other side. So this brings to this situation where your part, especially if the part is thick, is not so precise. So one solution here is trying to bend your cutting head. You can see here some other details of this situation. You can see here that the jet is not straight. But if you are able to model this, you can also compensate for this error because you can tilt your cutting head in the correct direction in order to save at least one side of your cut. Obviously you are saving your part and you are discharging all the error on the other side. So this is another point of evolution. There are machines on the market which are already able to do that in macro application, but there are no machines able to do this in micro applications. I will show you later the machine we are using for micro application, but that machine, even if it is very precise, it is a free axis machine, so it is not able to tilt the cutting head. We have carried out a model to tilt the jet, but in macro applications. So we would like to switch to micro also for correcting these very small errors on the corners. Here you can see some details. These are some details of the model we have carried out. So it is a kind of envelope, what you have to calculate. Once you have the envelope, you have also the trajectory which has to be followed by the top part of the jet. And by combining this trajectory to the other trajectory of the bottom part of your jet, you know the angle. And if you know the angle of your error, you can compensate by tilting the cutting head to the other side. Obviously, you have to do this in 3D. You can see here typical details. One very important fact is that you can see here that by applying this kind of model, you can make your walls straight, but striations still exist because the jet is losing energy when it is passing through your material. So there is no way of compensating the roughness. So typically, if you look at the Waterjet cutting curve, the bottom is rougher compared to the top part. In case you are using a large amount of energy, it could be that the difference between the top and the bottom is not so large. But this is because the jet, when it exits from your part, still have a huge amount of energy. So on the one hand, you are improving the quality if you are increasing pressure and energy, but on the other hand, you are discharging on your pool of your machine a very high amount of energy. And again, in case of very precise applications, this is not good because the temperature of the water inside the pool will rise and your machine will start moving a little bit. So it is very simple to lose some microns this way. Okay, you can see the non-compensated cut and the compensated one. Okay, some detail, but I can skip this. So, another typical point, as I told you from the beginning, is that the target could be to reduce the jet diameter. We can think about this point, because in reality, it is not needed to use a very small tool if you want to make something very precise. This happens also in milling. If you have to carry out one pin, it is possible to carry out also a very thin pin with a quite large mill. Obviously, we can enter into details of the geometrical characteristics of the mill in order to make it able to make a very precise operation. For example, the rounding on the edge of the mill is very important, not the diameter of the mill. Obviously, it is totally different in case you have to carry out 2 pins, because in that case you have to pass through the space between the 2 pins, and this could limit the diameter of your mill. But in general, the basic rule I have understood by being involved in high precision processes is that it is better to use the largest tool you can, every time you can. Also in milling, because I told you before that Waterjet has not a defined geometry, and I used as a comparison milling. But in reality, I am sure that you have already tried this, you have already seen this. Very small mill in reality bends, and it is quite typical in micro milling to cut in a banded configuration, banded fashion. So also micro milling can produce something similar to Waterjet on the corners. So for example, you have to be careful about the path in order not to make very sharp corners, also in milling. So in reality, when you approach high precision machining, there is something relating these 2 processes, even if they seem very different. But in some cases, you need very small tools. For example, we are trying, I have a PhD student working on this, to achieve this diameter for the final jet. Because in some cases, this enables new applications. So for example, applications in the electronic field. For example, we have to cut some slice of silicon, and in that case, a jet of 0.1 could be very interesting, comparing to the standard processes, which are diamond saws and so on. So these are the first attempts. So this is a prototype we have developed in our laboratory. You see that it is very rough, but I like this picture because, as you can imagine, these screws, well, I transform this in a question. What is the purpose of these screws, in your opinion? In the meantime, I calculate the time, so tell me when I'm too long. Why we have put these screws, in your opinion?
So adjustment of the nozzle.
Yeah. In particular, you have to align 2 nozzles. So you have here inside, you have the orifice, and here you have the focuser. And if you pretend to have a jet of 0.1, the risk is that even a very small error of alignment between the 2 orifices makes your energy completely useless. Because we have tried this, and even if you have a pressure of 3000 megapascals, and there is a misalignment, which is quite small, you are wasting your energy into it. So you are simply eating up your cutting edge. So as you know in mechanics, when you cannot be very precise from the beginning, usually what you can do is compensating. So this is a prototype, and what we have done here is to think about an adjustment procedure with some rules, because we had here 4 screws. It is not so simple to align with 4 screws, but it was possible. And here, finally, I can come to some cases. And these are the first cases developed at our laboratory. So here you can see typical characteristics of Waterjet parts. So this is a sandwich made of very different materials. what you risk here is the lamination. But if you think about a strategy where, for example, you carry out a drill here, a drilling operation here, and the drilling operation can be made by another process. So typically on high precision Waterjet machines, there is also a drill. So obviously you know the offset, and so first you carry out a drilling operation, then you can start with the jet in that position, and then you can enlarge your hole. When it is not possible, you have to very finely adjust your parameters in order to avoid the lamination. But I told you that Waterjet is flexible in terms of materials, and this is the demonstration. You can cut, for example, rubber, a layer of rubber, together with a layer of steel. And if you look at the surface finish, it is quite the same. This is because once you have overcome a certain threshold of velocity or a threshold of energy, which is needed by your target material in order to be cut, then the quality you can obtain on different materials can be quite similar. For example, this is quartz, 0.7 millimeters. The risk here is that even if the force of your jet is very tiny, the risk is that your part bends. And in case of quartz, obviously you break it. So this is a case where you have to invent some features. For example, you can use some layers of rubber on both the sides in order to prevent the bending of your layer. And in this case, we carried out also the holes.
So do you have any picture of the fixture?
No, but if you are interested in that, yeah, I can show you later. I have not in this presentation, but as I told you, this is a very critical part. And it is not general, so every time you have to change your fixture. And sometimes the difference between a good part and a wrong part is the fixture. So the companies able to carry out very difficult parts usually do not show how the fixture is designed. Consider that with feature I indicate something for resisting to the forces, which are not so high, and obviously the other typical target purpose of a feature is to keep the part in position. So it is a reference, for example, and so you apply typical mechanical concepts. But then you have to take the part in position, so you have to press it with something, and in this case, in the case before, you cannot directly act on a very fragile material. So you put another layer of another material. Obviously, you cut everything together, and obviously you are wasting material, but typically the applications are interesting enough under the industrial point of view to waste some material to the purpose. This is Kevlar. Kevlar is absolutely difficult to drill and to machine. Yes?
In the previous slide, you had quartz being cut, right?
Sorry?
In this one, you cut the quartz and you said you put rubber.
Yes, a layer of rubber on one side and on the other side. You make a sandwich, and then you cut everything.
So it's only to have more damping, or
yes, yes, to damp vibrations, and to have some layers of material which are able to bend instead of your target material. So if you apply with a fixture which is rigid towards a rigid part, you risk to apply the force in a very specific point, and your part will bend and break. So a very soft material is able to distribute your action on a larger area.
So basically it's only because it is brittle you apply
yes,
rubber?
This is one good solution. Sometimes the rubber is not enough. Sometimes you have to keep also in consideration that you cannot put together two materials which have two different properties. So sometimes you have you use a layer of aluminum, for example, which is softer comparing to very brittle or very hard material. We cut also ceramics, for example. And if you want to support ceramics, rubber is not enough. So it is better to have something which is not so soft. So for example, a layer of aluminum is good.
So for example, when the thickness of this part is, how is the thickness of this cloth?
0.7. I'm sorry, but it is not so.
0.7.
Yes.
So if you want to use aluminum, how much aluminum do you use as a layer?
I don't know. We are putting a light to your question. It's very important.
So I'm just asking if you want to use aluminum not to break the cloth.
Yeah.
How much aluminum, what thickness?
For example, 1 millimeter. 1 millimeter or 0.5
Okay, and both the sides?
on both the sides, yes. I don't know how to do. So. Okay, Kevlar. Sometimes the problem of Kevlar is the fact that you are producing burrs or you have some wires exiting your part, and this is not good. Waterjet can cut through with a very high quality here. And I think that this is one of the most strange part, the strangest part we have cut. So this is a sponge made of ceramics. So you can imagine how it is fragile. In this case, we cut through this part with these details by putting some material inside. So we developed a procedure. Now it is published. There is a paper dealing with this in order to fill the gaps, in order to compensate for the typical problem of the jet exiting in air, and in order to keep the jet straight. And in this case, we have been able to cut through all the thickness of this part, which was 15 millimeters. You can see some details here. Some biomedical parts made of titanium. Bones, these are real bones. Some colleague of ours in the department needed to carry out a specimen, and Waterjet can do this job very well. And in fact, Waterjet can be applied also in some surgery applications. You can see the details here. And then there are some applications that spin off. So this is the machine of the spin-off. I point out only these parameters. In this case, the machine has an accuracy better than 2.5 microns of the part. So in order to increase the capability of Waterjet, you need such a machine. Typically, the jet in the past was limited. Before I told you that the machine usually is not a problem, but the problem was commercial. So typical producers of Waterjet followed the typical applications like marble. I take as an example Italy. When you cut marble, you need an accuracy on the part of 0.1, 0.2. So they selected a handling system with not such a good precision. And then the company using Waterjet understood that Waterjet was not able to carry out high precision machining, but in that case it was the machine. But in that period, 20 years ago, 30 years ago, already existed some machines able to carry out these high precision parts. What happened is that it's something typical of non-conventional machining processes. If you think about EDM, the market asked for high precision from a process able to carry out this precision. And since EDM is able to work on a very hard material, it was very important for mold manufacturers. So in that case, there was a demand coming from the market for developing that process. In case of Waterjet, Waterjet is typically applied in some niches. So it took a longer time in order to arrive to a situation where it can be interesting in a very precise, very defined niches. And by this spin-off company, we are looking for these niches. It is not simple because many times you have to convince a company which is producing their parts with another process chain that Waterjet can substitute one or maybe a couple of processes. Typically, what happens is that some companies are using lasers. I'm in general, and in this case, I'm not dealing with a specific laser source, but this is quite typical because everybody knows that on a very thin layer you can use laser. But laser, if you're not using the correct source, or in case you want to be very fast, which typically happens in the companies, is damaging the border, so the edge. And then you have to carry out some thermal treatments or some other machining operations in order to take away this material. Sometimes this happens also in EDM. In case of Waterjet, usually, since it is a cold process, sometimes you can carry out your part in only one step, in the sense that you don't have to treat the part after cutting. So very strange combinations of materials. This is marble combined with a sheet of carbon fiber. This is used from a producer of glasses. You know that designers are very able to combine in a very strange fashion materials, and then somebody has to cut these kind of combinations. Waterjet can do that. Or another typical application is prototyping for blanking operations. You know, when you have to develop parts from the automotive field, you have to develop also the mold. But the mold is very expensive, and in the first design phase, you want to modify the part. So high precision Waterjet can substitute blanking on small lots. So this happens. Many times happens that the companies working in the automotive field are asking us for carrying out some prototypes. Yeah, very thin layer, very thin walls. In this case, it was titanium. Or other strange materials, Vetronite. This is not conductive. So in this case, obviously, you cannot use processes like EDM. Or glass. You can see here some details made on glass. Glass with a thickness of 1 millimeter. And everybody knows that glass is absolutely fragile. And you can see here the frame. Yeah, you were asking me a kind of frame. So every time we have to cut a specific frame in order to host the parts. And in order sometimes to avoid the typical defect in Waterjet, but also in wire EDM. Because when you close the cut, you have a specific defect called bridge. And the bridge is sometimes something which is not accepted by your application. So you have to invent something in order to be able to cut through also the bridge after the function correctly carried out by this bridge. Titanium. So I think that this is an example in order to compare high precision Waterjet to femto laser. If you can see here, these are 12 millimeters. You cannot do this with a femto laser. Or if you do it, you take a much longer time. So the niche of application of high precision Waterjet is something in the middle between laser, femto laser, and on the other side, wire EDM. In the middle, there are some applications where the material is not conductive, for example, or the material is has a thickness which is in the middle, or the required tolerance from your part is not so precise to require an EDM, wire EDM operation. In that niche, Waterjet can act. I think this is the smallest part we have cut. So this is a composite material. This is also a magnetic material. There is a hole here. and the diameter of this hole is 0.4 millimeters. The tolerance, which is not written here, was 6 microns. And these are other applications. This is metal sheet. This is inox stainless steel with a thickness, if I'm not wrong, of 0.5 millimeters. And typically, the tolerance which is required here is something ranging from 0.01 millimeters to 0.03 millimeters. So this is quite typical. This is copper, so these are electrical connections. You can see the first phase where you have to drill and then you go on with the cut. Obviously, you have to carry out first of all the holes and then the periphery of your cut. Okay. Yeah, these are hybrid machining operations where the idea is to carry out a roughing operation by means of waterjet milling when you have a very hard to cut material, like, for example, again, titanium. So you carry out a very deep pocket, which is quite difficult for milling operations, and so you take away the most part of the biggest part of the material, and you obtain something like this, and then you carry out a finishing operation by milling. Okay. And now, yes, I would like to switch to the other presentation, where I don't think I like to show you something about that. Yes. So, this is the orifice. As you can see, the orifice in reality is only the stone. The stone is made of sapphire or diamond. So everything happens here. So the diameter of this hole can be 0.3 millimeters, or in case of micro waterjet applications, it can be 0.05, so 50 microns. So this is the Bernoulli equation, so I think I can go quite fast here. And you can apply some hypotheses, because the water is quite, has no velocity upstream the orifice. And we can consider that also the pressure after passing through the orifice, as I told you, is quite negligible. And also the difference, or in general, the dimension of the orifice is not comparable. So the potential energy, depending on the thickness of your part, is not comparable to the energy of pressure. So this way you can arrive to this very well-known formula for the velocity. So this is an uncompressible velocity. But the problem here is that we need to consider that also water can be compressible at a pressure of 300 megapascals. So you have to consider the diagram of the water, and you have to consider the relation between pressure and density. If you apply this, you can have a formula describing what is happening to your velocity in case you have to consider that the water is compressible. So this is the compressible velocity. This means that you are wasting some energy in order to compress water, and the velocity you obtain is not the same as in case of uncompressible velocity. So, for example, you can note here that the density in case of a pressure of 300 megapascal increases of 10%, so it is not negligible. So this is why we have to consider a compressible velocity. Then, these are the nozzle coefficients. Every time you think about waterjet, you need to understand the performance of your orifice. because you can find on the market sharp-edged orifices. You can find rounded orifices. In order to characterize the orifices, you can use the coefficients. So if you compare the compressible theoretical velocity comparing to the Bernoulli velocity, you obtain the compressibility coefficient. Compressibility coefficient in reality is not an efficiency coefficient, because in reality you are not wasting energy. You are using energy in order to compensate for the compressibility of water. This is something natural. Where you are wasting energy is here, so with the velocity coefficient. So in this case, you obtain a velocity here downstream the orifice, which is less than the theoretical compressible velocity, because of the streams, of the streamline of your water jet, because it is not a quasi-static transformation, as you can imagine. And in this case, you lose a couple of points, percentage points here. But which is more important is the contraction coefficient. If you have a vena contracta after the orifice, this means that the diameter of your real your real jet is less than expected. So you are discharging less flow rate. And so again, we could discuss if the contraction coefficient is something related to efficiency or not. What do you think about this? Are we wasting energy because of the vena contracta, or simply we are not asking for this energy? What do you think? You know what I mean? The jet has a vena contracta, so the diameter of the jet is less than the nominal diameter of the orifice. And consider that the contraction coefficient can be 60%, 0.6. So is this meaning that you are wasting 40% of your original energy? In case it is like this, the cutting edge of Waterjet would become very, very hot, because the power of your pump can be 50 kilowatt, and you cannot discharge in it 40% of 50 kilowatt. So simply your jet or your orifice is not asking for that energy. So it is like the orifice is smaller. So by combining these orifices, you have the discharge coefficient. So the discharge coefficient is the one relating the theoretical flow rate, as you can see here, Bernoulli velocity multiplied by the nominal surface. And if you multiply with this by the discharge coefficient, you can obtain the real flow rate. Here, you can see here another typical physical quantity. So this is the hydraulic kinetic power of your jet stream. You can see the typical part. So you have the velocity of the jet, and you have the mass flow rate. If you make the calculations by using the orifice coefficients, and I do not intend, obviously, to comment about this, you have a final formula. I point out only this part on this formula, because if you see the characteristic of all these parameters, these are all constants, because they depend on your orifice. So once you have defined your orifice, this is all constant. You can see here that the kinetic power of your jet stream depends on the diameter, the nominal diameter of the orifice at the power of 2, and it depends on pressure at the power of 1.5. I think this is quite interesting, because a typical question is it better in your opinion, to push on the diameter of your jet or on the pressure of your pump if you want to improve the cutting capability? If you look at the exponents here, you can decide, because the diameter of the jet is more effective, because you have 2 here compared to 1.5. So this means that it is better to have a larger orifice, so it is better to buy a more powerful pump and not to buy a high pressure pump. It makes no sense to increase the pressure in general. But I want to arrive to the point where we can understand how, in reality, in micro machining operations, it is better to increase the pressure. So this is my target. We can make the balance then considering the masses you have. So you have water, abrasive, and air, because everything goes to the cutting head and mixes. The energy comes from the water, and it is distributed to air and abrasive. So these are the input parameters. And here you can see the output parameters. So this is the velocity of the mixed jet. So this is the jet which contains air, abrasive, and water. We can neglect the mass flow rate of air because of the density of the air. So if we consider this balance, we can make some calculations, and we can arrive to a very simple formula here, which allows you to calculate the velocity of the mixed jet starting from the velocity of the pure water jet by simply considering this ratio. This is the ratio between the flow rates, the flow rate of the abrasive compared to the flow rate of the water. And if you consider a macro machining operation, typically you have half a kilogram per minute, which is going to your cutting head. And typically, a typical pump of water jet machining can discharge 3 kilograms per minute of water. So this way, you can calculate quite easily the velocity of your mixed jet by starting from the velocity of your jet. And by using the orifice coefficients, the velocity of the jet is quite simple to calculate again. If you look at here, we can understand that the velocity of the mixed jet is 85% in this case, which is quite usual, comparing to the velocity of the pure water jet. This is because the water has given its energy to these 3 means, but obviously only one of these means is able to cut, which is the abrasive. And this is the hydroabrasive power. So you remember that we have calculated the pure water jet power before, but if we mix also the abrasive, the correct formula to consider in case of abrasive water jet is this one, where we are considering the mass flow rate of water and abrasive. We cannot neglect these 2 terms. If we make the calculations based on the equations before, and I pass through the calculations because again I want to come to the point, we can see that part of this formula, and specifically what you see in brackets, depends on what you see here. So you have pressure with an exponent of 0.5, and the diameter of the orifice with an exponent of 2. But then you have to multiply these terms in brackets by the velocity of the mixed jet at the power of 2. And considering this, you have to add here another pressure. So again, you arrive to the same condition. So the point here is that both the kinetic power of the pure water jet and the power of the mixed abrasive water jet depend again on the same parameters: diameter of the orifice with an exponent of 2 and pressure with an exponent of 1.5. So same considerations. So this means that this approach is quite general. I'm coming to the last part of this discussion. I like this discussion because Q-mat sometimes is called material mover rate. I think you have to manage this quantity, because when you compare processes, I think this is one of the best performance, or the most important performance you have to consider, because this means productivity. So this means how many parts you are able to obtain in a unit of time. So you can compare processes by looking at this. And this is very physical, because this equation is saying that each material has a certain amount of energy, volumetric energy, which is needed to take away the material. So if you have studied other machine processes, you have seen that, for example, in, again, milling or chip removal processes, you have the cutting pressure. This is the cutting pressure, because cutting pressure, the physical meaning of cutting pressure is a specific energy to take away that volume of the material. So again, this energy is related to the material. And in effect, you can obtain this by looking at some characterization tests. So this is something you can obtain from other tests. And this is something quite general. What you are doing is using the power of your mixed jet in order to take away material. And so if you have more power, you are increasing the material removal rate. And this happens, as I told you before, in both the cases. This is the case of pure water jet, and this is the case of mixed jet, where, again, we can see that the functional part is only this one, with the same exponents. So if we look at the way we are using the energy, we can consider that the material removal rate can be considered as something quite simple. This is the width of your cutting curve at the top, and this is the width of your cutting curve at the bottom. You can calculate the area of the section of the cutting curve, and this cutting curve has a depth of h max. This is the maximum cutting depth. By using this formula, we are calculating, again, the section of your cutting curve, which moves ahead at the velocity equal to the feed rate of your cutting head. So this is a very simplified way of calculating the material removal rate, looking at the part. So on one side, we are looking at the part, and on the other side, and on the other member of the equation, we are looking at the power we have. By applying some simple hypothesis, for example, we can consider that the cutting curve is straight, which happens in high precision machining operation. We can come to an equation like this. So this is the original one, and this is the calculation we have done looking at the part. So diameter of the orifice multiplied by the thickness of your part. So we are calculating a squared section for your cutting curve, multiplied by the speed, the cutting feed rate of your cutting head. On at the second member, we have something depending on pressure and diameter. All the rest are constants. So when we arrive here, I point out specifically this equation. So I'm passing through, I start from this equation and I come here. What I have done here is considering that these two terms together make the power. And the power comes from your pump. So it is a design topic. So once you have selected a certain pump, your pump has a certain power. So what we can do is using your pump at the best. So it is something fixed. So once you have that pump, if you are able to select the parameters, and so I'm coming back to your preliminary question, the best you can do is to maximize the power you are asking to your pump. So in reality, these two terms together are constant. And then we can see here something interesting. The diameter comes here at the second member. So this is interesting because we can make two considerations. One is that in reality they are coupled. Let's think about an application where you have a very small diameter because you want to carry out a specific part and you have to pass through two features and you need a very small jet. The example is MEMS. You have to separate some MEMS and you need a jet of 0.1. Obviously, what we can do with Waterjet is cutting the silicon layer. And in order not to damage the MEMS, the circuits, you need a very small jet. So this is small, and everything seems seems completed in the sense that if you look at this formula, this is a constant, and since your jet is small, you are maximizing these two terms. So you can maximize the cutting speed, you can use this energy in order to go very fast, or if you can keep this cutting speed, feed rate constant, and you can use your energy to cut very deep. So this is the use of this equation. But we are neglecting something, because in reality, if you think dn as a variable, so you think to reduce dn, in reality you have to compensate for the power of your jet, because if you are reducing the diameter, you are losing also power if you keep the pressure constant. Are you with me? If you look at here, this is power. If you reduce this and you want to keep this constant, you have to increase pressure. And this is the game of micro Waterjet application. You reduce the N and you increase the pressure. So this is, in my opinion, the only case where it is convenient industrially and commercially and economically to buy a high pressure pump. So you can find in the market pumps with 6,000 bars. But be careful with those pumps because they are not reliable. But I have to say that in case of micro Waterjet application, you need that pressure. And sometimes it is good to risk. And this is the force which is pushing towards high pressure pumps. So micro is the reason why it makes sense to have high pressure pumps. For all the rest, the best of Waterjet is using large orifices. Okay, so I think you have we are at the end also of your patience. Tell me.
The pumps that you've been investigating that were supposed to deliver 6,000 bars, how much did they deliver then?
How much? Sorry?
You say that they were not reliable, therefore I assume that they've been supplying less pressure than they actually claim. How much less was it?
No, I was not using reliable in that sense. The sense is that the parts are subject to such a high pressure, which is absolutely beyond the capability of your materials. So the tubes, the pipes, for example, they are subject to autofrettage in order to make them resist to such a high pressure, but they do not resist to a high value of cycles, a high number of cycles. So economically it is not convenient because you have to spend a lot of money in maintenance. If you compare this with the standard Waterjet pump, which achieves 4,000 bars, which is already quite high, That kind of pump can work 24 hours per day and 7 days per week in a very stable fashion. So it is not comparable under the economical point of view. But since we are involved in micro applications, I say that maybe it makes sense to buy a 6,000 bars pump and use it at 5,000, which is better than the standard. And this is a situation which is not pushing your pump at the limit, which is very risky. Consider that an high pressure pump of 6,000 bars is very expensive, so 150,000 euros, which is 3 times the cost of a 4,000 bars pump. So it is very expensive on your part. You are never able to compensate for such a cost. But I think that in case of micro applications, in case we altogether are able to find new applications, and things are getting better also for the spin-off company, it makes sense. A couple of minutes. This is the characteristic curve of the pump. So when I said that you have to use all the power your pump is able to provide, it means that you have to work here at the knee of this curve. This is the point where you are using the maximum couple of flow rate and pressure. These are the ISO power. So you have to stay here. So if this power is not enough for you, you have to design another pump, or you have to buy a pump with another characteristic curve. Okay, let me see. Okay, let me conclude with 2 slides. This is the real part I have already commented before. This is the drawing. So, as far as I know, at least in our laboratory, but in general on the market, this is the most difficult part cut by a Waterjet machining operation because of the tolerance. And because of the fact that it is absolutely tiny, so very difficult to manage. And this is also magnetic. So once you have cut this part moves. So this is absolutely difficult. And look at the characteristics here. Okay. We have written a chapter in this book, so you can find something about what I have commented here today for you inside the chapter here. And obviously we have published many papers on all these points. So if you are interested, I can give you the PDFs. So simply ask me. So if you have some questions, I'm here. Also later if you want. Otherwise, I think I have been 5 minutes longer.
You can take 5 minutes if you need to conclude, but that's...
No, I would be happy to answer to questions if you have.
Great.
Thank you.
Another thing, like after the process, the water and with the abrasive is just discarded, or somehow you reuse it in the process, or anything?
Yeah. The water has to be controlled. There are a couple of ways. One way is to make it softer. You have to take away calcium and various elements like that which risk to deposit inside the tubes, and they risk to damage your piston.
Mm-hmm.
On the other side, you have to take away also chlorides, because they are very detrimental for the stainless steel parts of your pump. But you don't have to exaggerate. Otherwise, if your water is too pure, as in case you use inverse osmosis, which is the other solution, in any case you have a risk. So the water can be aggressive on both sides. So if you look at the data sheet of the pump producer, they tell you what you have to do in order to characterize your water. The other part which suffers, considering the water, is the orifice. All the orifice is very fragile, so if you have some particles inside your stream, they are damaged. So this is quite typical at the beginning when you ramp up manufacturing operation, or you ramp up a new plant. You throw away a lot of orifices because of the particles. Regarding the water, what you have to consider is typically metals that you are cutting. So sometimes the target material is dangerous. So in that case, you have to separate the slurry you are producing, because at the bottom of your pool you have a slurry made of abrasive and also metals. So in that case, you have to be careful. But if this is not the case, so if the metals you are cutting are not aggressive, you have to think that you are using only water and sand at the end. So yeah, you have to deal with this problem, because you know that the laws are stricter and stricter, so you have to consider this. But comparing to other processes, for example, like chemical processes, it is not comparable, so it is less dangerous. And another typical question like this is the abrasive recycled or not? This depends on simply on the cost of the abrasive. So it depends on the market again. Sometimes it happens that due to commercial reasons, the abrasive becomes more expensive, and in that case it makes sense to recycle. But the problem is that, again, the metal inside the abrasive. In case you want to organize a service for recycling the abrasive, if you are a seller of abrasive, you have to consider what material your customers are cutting. So if you are sure that you have a certain amount of companies which are your customer, and everyone is cutting aluminum, okay, you can put everything together and you can recycle. But the equipment you need to use is similar to the one used for concrete. So it is a huge equipment. So it is very difficult to manage. So usually it is not recycled. Yeah.
What types of abrasives we use? Is it like silicon dioxide, silica, and
yes,
what
exactly.
other? Do we have specific abrasives for specific materials?
Yes, this is a good question. Again, for commercial reasons, the most applied abrasive is garnet. So silica, garnet is the name.
Okay.
So they are oxides of silicon and oxide of iron and so on. In some other cases, we have also used the sand used in foundry, olivine. Olivine is another kind of abrasive which is less aggressive. But the problem of abrasive is powder, because the powder clogs, risks to clog your pipes. So the most important characteristic of the abrasive is the distribution of the granulometry. So the more your bell distribution is narrow, the best you can find on the application. So For example, Barton Garnet, which is a brand coming from US, is very expensive. It reached about €1 per kilogram, but it is very well separated, so you don't have powder inside. What we have found is that if you put your abrasive in a very dry condition, you can obtain good performance. So even if they tell you that it is not hygroscopic, in reality, you have a part of water together with the abrasive. Obviously, abrasive will see water, but this has to happen only inside the cutting head, not before. If it happens before, you clog everything. So what we have found is that a good quality of garnet is the one coming from, for example, from India, which is quite cheap, but it is enough. In case your application is very challenging, it is good to spend €1 per kilogram, only when it is worth.
The second question, can this Waterjet be used for injection mold tool grinding and design?
Used for, sorry?
Injection mold tools. So we use grinding for micro features or some micro cavities. Can we use Waterjets to prepare such tools of injection molding, micro injection molding?
What you can do is using Waterjet for deburring. So this has been already done by using a soft and non-aggressive abrasive. So in that case, you can take away the burr. But what you are asking for is something like milling. What I call it milling. And maybe you have seen the quality. The quality is quite bad. So this is because we think that it could make sense for a roughing operation.
Okay.
Otherwise, you can be very soft. It is something like sanding. But yeah, it is another process. It is not Waterjet. Okay, in any case, if you have other questions later, contact me.
Sina will be with us until tomorrow, so we'll have
Okay.
plenty of opportunities to ask questions.